Hey, welcome to this Rational Function 2 video part 2 on rational functions. This example right here on the top of the screen represents a little bit more challenging type of question. Why? Now we're dividing a linear polynomial by a quadratic polynomial. So there is a difference in degree. In the last video we said let us examine questions with two identical degrees. Now the difference is 1, so the bottom has greater degree than the top. So first thing you do is your domain. Okay, you find the domain. That's the first part. You want to identify what values of x are allowed to be used for my question. Excellent. So since 2x squared minus 5x minus 3 is equal to 0 is a quadratic equation, we have an option to solve it by factoring. So the two numbers that multiply to -6 and add up to -5. Where -6 comes from? 2 times -3 gives me -6. So the numbers are -6 and 1. What we will do now is replace the middle term, -5x, as -6 plus positive 1x. And then by grouping, please note that 2x is a common factor for these two guys, and x minus 3 will stay without any changes made to it. So 2x pulled outside gives me x minus 3. And now, by adding x minus 3 here, I have two identical factors, x plus x minus 3 and x minus 3. So this goes out right here. Okay, and now I have 2x plus 1 is equal to 0. So the result for that is x is either 3 or -1/2. So I have two restricted values in the domain, which means possibly there are two vertical asymptotes here, possibly. And further down on this side of the screen, as you see, if I rewrite the denominator as a product 2x plus 1 and x minus 3, all of a sudden I see two identical factors. So by reducing this expression, now we get a different, seemingly different type of function as opposed to what we saw in the beginning. However, the degree difference is still 1 because the top is 0, the bottom is 1. So the denominator is of greater degree than the numerator, which should remind you of a function from part 1 video, a rational functions where the top was constant and the bottom was a linear expression. So what happened with two vertical asymptotes? Since 1 was reduced, 2x plus 1 expression was eliminated, so -1/2 is gone. So the only vertical asymptote that we have here is the one at 3. So that's the only vertical asymptote. And what happens to the other value of -2? This becomes a point of discontinuity, and when x is equal to -1/2, the y value is -2/7. This comes from basic substitution. What you do is find how much is f at the -1/2 using the simplified equation, not the original one, because using the original would not get you anywhere. You would get 0 divided by 0. So this is why you use the 1 over -1/2 minus 3, and in the process you're going to get -2/7. So this is where y coordinate is of that donut hole, of that point of discontinuity. Okay, so now we'll have to find x-intercepts, y-intercepts, and create a graph. Okay, so this is where our attention now is on the new equation of this function in simplified form. So since the top degree is 0, the bottom degree is 1, so we expect to have one horizontal asymptote at 0. Always remember the following rule. If the top degree is less than the bottom, there is only one horizontal asymptote when y is equal to 0. So this is explained in this little paragraph here, and our asymptote is expected to be at that position here. X-intercept. So there's no x-intercept. How come? Because if the top value is 1, so there's no value of x that will give you that result when you divide two numbers and the answer is 0. If you were to use the unsimplified form of this equation and set it equal to 0, you would have to find out that 2x plus 1 is equal to 0 when x is equal to negative 2 and negative 1 over 2. But negative 1 over 2 is a point of discontinuity, so this is why you cannot cut through this point at all. Y-intercept, when x is equal to 0, you get the reading for y, and that's the point of y-intercept. Now, the graph of this function. So look at this green line. We have a horizontal asymptote at 0. We have vertical asymptote only 1 at 3. And now you see this graph is discontinuous at that point where x is equal to negative 1 over 2. So this is the point of discontinuity. It would have been if the question was not simplifiable, this would have represented another location of vertical asymptote. But since our vertical asymptote was reduced to that one point, so this point is the point of discontinuity. The graph does not exist here, so there is no y value. If you were to replace x with negative 1 over 2 into the original equation, or even if the simplified equation, you can't really sub it in because of the domain. The domain says not equal to negative 1 over 2. So practically you cannot use that point to calculate the value of y. You can do only for the purpose of finding coordinates of that point of discontinuity. So remember, this is very, very important. Positive and negative intervals. So look at the graph and observe the following. X is less than negative 1 over 2, that donut hole. Also, x in between positive 3 and negative 1 over 2 is where the graph entirely is found below x-axis. So this implies that f of x is less than 0. So this is the interval where the function is negative. And on the opposite side, with respect to the vertical asymptote, we have now for x's that is greater than 3, all values are positive. So the graph is found above x-axis. Increasing or decreasing intervals. Just look at the graph and observe that as you read it from left to right, you have to observe that you're sliding down. So this is where you continuously decrease on its entire domain. So we can conclude that this function is decreasing on entire interval. So the next example will be a little bit more challenging than this one. Okay, I see you in a bit. Okay, now this example is very, very similar to the previous one. Why? The top has degree 1, the bottom degree is 2. So yes, we'll have a horizontal asymptote at 0. Agreed on that. Excellent. Now, by factoring it, the denominator, because this denominator is essentially the same as the one from the previous example. So this is why we know that there are two factors, 2x plus 1 times x minus 3. The top this time is 2x minus 1. So we can't simplify this. So this is the case where you have two restricted values at -1/2 and 3. And now you have two vertical asymptotes. Not one, but two. Okay? So this is where we see two restricted values with two vertical asymptotes. So there will be two vertical lines dividing that rational functions. Horizontal asymptote, we have just mentioned that, will be 0 because the difference in degree is that the top is less than the bottom. X-intercept and Y-intercept. So let's find that. So how do you find x-intercept? Simply solve the numerator, set it equal to 0, and get the number. So that's the equation right here, which will lead to the statement 1/2 and 0. Y-intercept, set 0 into this equation, and you will get 1/3. So the graph now will be shown here on the grid right here. Okay, the green line. So the discontinuity is only found at vertical asymptotes. So we have one y-intercept, one x-intercept, two vertical asymptotes, and that's the graph of this new rational functions. So now, in a moment I will show you how we generate the graph by using some test values. So that will be shown in a bit. Right now we'll concentrate on positive and negative intervals. So define the x values where y is greater than 0 or less than 0. So what you see here is the following. As x is less than -1/2, we have to grab a different pen. So x is less than -1/2, and also from 0, 1/2 to 3, and also x is in between 1/2, which is the x-intercept, and 3. So these two intervals give us negative reading for our function. The positive reading is the remaining intervals. Obviously, you have to sort of complement the set of real numbers. So positive is when x is greater than -1/2 and less than 1/2. Also, there is one more interval when x is greater than 3. Is this function increasing or decreasing? So pretend that you're walking along and you see that you have tendency of decreasing the value of y. So this graph is also decreasing on entire domain. So this is only this portion here. F of x is decreasing in its value on entire domain. Okay, so I'm going to show you now the way of finding the graph by using certain test values. So this is what you do. Your x-axis, your set of real numbers, is divided into several intervals. Okay, so we have one interval here, which is found between -1/2 and -infinity. So you grab it, so this is the interval right here. You get a test value, any arbitrarily set number, as long as that number is found on that interval. So -1, you find the value of the function when x is -1, and this gives you negative reading. So this is why you expect to see the graph below x-axis. -1/2, this is the little circle here showing that this is not part of the graph, so there's discontinuity here. So this is why the circle remains open. The test interval now is between -1/2 and 0. So you don't want to sort of miss that possibility of changing its sign. So this is why you see -0.5 to 0. Select any number that fits into that interval, plug in, you see positive. So this is why the graph is above x-axis. Between 0 and half, same story. Plug it in. Where do you plug it into this formula here? Use that equation in its original form. Okay? And you test this interval. You have negative reading, so it's right here. And finally, greater than 3 interval, and you have positive reading. So this is behavior of the function, whether it's also this exercise can be used to find positive and negative intervals, and also you can use that information to create the graph of a rational function. So I hope that you really enjoyed watching this video, and I want you to go and post comments, ask questions, any questions that you have, and like that video. Thank you very much for watching, and I see you next time. Have a good day. Bye-bye.